Hello, welcome to lesson 33. Yes, this is a mistake, so I want you to cross out the number 31 and put 33. So this is lesson 33. We will be going over section 4.4 from the textbook, which is all about comparing many means. So you are encouraged to read pages 184 to 195 in the textbook. Sometimes we want to compare means across many groups. We might initially think to do pairwise comparisons. For example, if there were 3 groups, we might be tempted to compare the first mean with the second, and then with the third, and then finally compare the second and the third means for a total of 3 comparisons. However, if we have many groups and do many comparisons, it's likely that we will eventually find a difference just by chance, even if there is no difference in the populations. So far, we have discussed the normal. So I'm going to remind us that the normal uses p or difference of proportions for our class. We've been using the normal distribution for proportions or difference of proportions. We've been using the t distribution for means or difference of means or the mean of the differences. And we've also talked about chi-square distributions. And those ones compare many proportions. We've been using that to compare many proportions. So to compare many means at once, we will need to consider one more distribution, which is called the F distribution. Like the chi-square distribution, the F distribution is always positive and skewed right. However, this distribution comes from the ratio of 2 types of variation with 2 different degrees of freedom. When we want to compare the averages of many groups, we will use the following hypotheses. So the null hypothesis will say that all population means are equal to each other. The alternative hypothesis will say that not all of the means are equal to each other. And this little note down here says, in the event the null hypothesis is rejected, this test won't tell you which mean is or which means are different. Additional tests or confidence intervals must be performed. Here's example 1. Suppose that we want to compare the averages of 3 groups. So the null hypothesis would say that all 3 means are equal, and the alternative hypothesis would say that not all of the means are equal to each other. List all of the possibilities for the alternative hypothesis. Okay, well, if not all of the means are equal to each other, then maybe it is the case that the first 2 means are equal, but the third one is different. Or maybe the first and the third are equal, but the second one is different. Or maybe the second and third are equal, but the first one is different. Or maybe all 3 of them are different from each other. So rejecting the null hypothesis will mean that one of the 4 possibilities here are likely true, but other tests would be needed to narrow it down further. Here's example 2. College departments commonly run multiple lectures of the same introductory course each quarter because of high demand. Consider a mathematics department that runs 5 sections of an introductory statistics course. We might like to determine whether there are statistically significant differences in first exam scores of these 5 classes. So we will label these classes A, B, C, D, and E. So it says describe appropriate hypotheses to determine whether there are any differences between the 5 classes. So the null hypothesis would say that the mean of class A equals the mean of class B equals the mean of class C equals the mean of class D equals the mean of class E. And then the alternative hypothesis would say that at least one mean is different from the others. So we're going to talk about something called ANOVA, but I want us to recall that variance equals the square of the standard deviation. So ANOVA, which is the analysis of variance, is used to compare the means of at least 3 populations. Use a 2-sample t-test to compare the means of 2 populations. The ANOVA procedure for comparing these means involves analysis of the variance in the sample data. Generally, we must check 3 conditions on the data before performing ANOVA. So number 1, the observations are independent within and across groups. So what that means is that we want to see that it's a random sample and it should be less than 10% of the population. Number 2, the data within each group are nearly normal. So what that means is that there are no outliers and that it has manageable skewness, not too skewed. And number 3 is that the variability across the groups is about equal. When these conditions are met, we may perform ANOVA to determine whether the data provides strong evidence against the null hypothesis that all the means are equal. As its name implies, ANOVA uses variances to complete the test. ANOVA separates the variance among the entire set of data into 2 categories, called the variation of groups and the variation of error. The F distribution is then used to compare these 2 variations. The first category is the variation between the different levels being tested. This is called the variation of groups. Think of this variation as the treatment effect. So over here we see two box plot graphs comparing side by side. On the left we see a large variation of groups, and on the right we see a small variation of groups. So a large variation would likely result in rejecting the null hypothesis, whereas a small variation of groups would likely result in failing to reject the null hypothesis. The second category is the variation within the levels being tested. In other words, the consistency. And this is called the variation of error. Think of this as a measure of precision. So we see two box plots side by side again, and on the left we see a large variation of error, and on the right we see a small variation of error. So a large variation of error would show really elongated box plots, whereas a small variation of error show short, condensed box plots. If the variation between the groups is significantly more than the variation within the groups, or the error, then the means are considered unequal, and the null hypothesis is rejected. So over here we would reject the null hypothesis. We see the box plots are very spread out, even though they are condensed. And over here we would fail to reject the null hypothesis because they are not very spread out, even though they are pretty condensed, but they're a little bit longer than these ones over here. So that's the difference between the two. Here's example 3. So we are asked to compare groups 1, 2, and 3 below. Can you visually determine if the differences in the group centers is due to chance or not? Okay. So what I'm going to do here is I'm going to mark where I would consider the balancing points are. So pretend that all of these are, I don't know, weights or people, and if they were all standing on a board that needed to be balanced in the middle, where would I put the fulcrum of that balancing board or seesaw? I might put the balancing part right here for the first group. I might put it right here. So it's not so much that we have equal data on either side, but we have to also notice the distance that things are from the center. So if you have a lot near the center, that's really not going to weigh this side down as much as if you have things farther from the center. And then probably the balancing point over here might be maybe, I don't know, about right there. So this is just me guessing, using just visual cues to notice where the balancing points are. So because the balancing points in this side of the graph are fairly similar, we would probably fail to reject the null hypothesis for whatever this is measuring. Okay, now let's take a look at the right side. Okay, and I'm going to try to mark the balancing points for these. So this one might be about right here. Maybe this one is a little bit up here. And then maybe this one is about right here. Okay. And also notice that there's nothing here for this middle one. All the points are kind of really close together here, but they're not spread out over here. So here there's nothing. So these balancing points look a little more spread out than the first group's balancing points. So because of this middle one, we might have enough evidence to reject the null hypothesis. And also, just to be clear, these plots obviously are not box plots, these are dot plots. So here's example 4. The graph below shows commuting times for randomly selected drivers in 6 cities. Graphically test whether the average commuting times are the same. We'll look at the numbers in our next class or next lesson and assume the conditions are met. Okay, so I'm going to go through and kind of mark where the middle line is. So remember, with box plots, the median is this line that is going across the box. So I'm going to highlight those in each box plot. So if you were to compare those lines, I mean, they're pretty even, except for maybe this one, this first one, is the one that is most different from the others. So we might say that we're not sure if Atlanta might be enough to reject the null hypothesis.